fixed it, so it's coming through my headset now and not my laptop mic. What are we doing? Hopefully. Anyone here? I'm gonna wait a minute, see if some people show up, talk about some integrals. I want to make a drawing. It's a dog. I think I was in 3rd or 4th grade. I was playing at the softball field near my house, and a girl named Melanie taught me how to draw this dog. And I still draw this dog when I feel like drawing something. Which is usually at the start of class. Am I live? My phone's not seeing me. If I look me up on another browser, does it see me? Let's search YouTube for Andy Yingst. There's me. 74 videos, jeez. Yeah, it says I'm live now. Yep, I'm live. Who's watching? Me, I'm watching. Nobody's watching. I asked my class to show up and watch this one live, and nobody did it. Hey! Somebody showed up. Are they? It's not showing here on my list of viewers. Well, somebody showed up. I guess that's enough to start doing some math. Let's do some math. So our goal, like we've talked about all these techniques of integration, and I want to, like, the thing is, when you get your exam, I'll post the practice exam after class today so you can see what it's going to look like. But it's just going to be a list of integrals. It's going to say, hey, here's, the way I like to do it is I'm going to say, hey, here's 11 integrals, do any 9 of them. There's kind of 2 options. I can either say, hey, here's 11 integrals, you get to choose and do 9 of them, but if I do it that way, I'm going to throw in one that's impossible. Because part of the deal is not every integral is doable, and you need to be able to recognize these are the ones I can do. The alternative is I can say, hey, here's 9 integrals, do all of them. The price you get, the reward you get for me throwing in an impossible integral is that... Uh-oh. Someone's not seeing it. The reward you get for the impossible integral is you get the option to say, you get the option to say, hey, I'm not doing this one. But the penalty is the psych out of having one that's not doable. And I don't really care either way. I'll let you guys vote once more than one person is here. Let me see if I can find a link to the video that I can stick in the chat. My texting is on phone, so I need to look up the video on my phone, which I do by going to the YouTube app. Cool. Yeah, sometimes I don't know why. Sometimes you go to a video that you know is streaming, a channel that you know is streaming live, and the live thing doesn't show up. Okay, a question I want you to think about. Would you rather? What's better for... What's your preference? Option A. So, what's your preference for an exam? Option 1. Here's 11 integrals. Choose 9 to do. But 1 is impossible. So you need to avoid the not doable one, but you get to also avoid one that you just don't like. Option 2 is here's 9 integrals, do all 9. Which of these do you prefer on an exam? You can answer your preference right now, but I'll wait until you've looked at the practice exam and see what this looks like in practice. Alright, let's do some integrals. I'm going to write down 3 integrals. Pick one and tell me what would you do to do this. Here's an integral. Here's an integral. Cool. I like option 1 too. Mostly because it's more fun. Like, it makes more of a game out of it. Say you're in an exam, you see these 3 integrals. Which one are you the happiest to see? Which one do you know how to do right away and you know for sure that the thing you try is gonna work? I'll give them letters to talk about them with. How would you do problem A? Hey, I got 4 people watching. That's like a whole dang class worth. Awesome. I'm happy to have some evidence that somebody's watching at all. Nobody's asked me any homework questions yet. How do you do problem A? Or what's the first thing you would try? Are you certain the thing you would try would work? And what do you want U to be in your U substitution, Caleb? Boy, this lag makes communication difficult. Yes, U substitution is the perfect thing here. This is sort of a good tricky question to stick on an exam like this, because people who've learned trig substitution look at this and think, hey, this is a good trig substitution problem, and a trig substitution will work. The trig substitution will be x equals tangent theta. Dx is secant squared theta. That works. But the U substitution is way cleaner and nicer. You want U to be x squared plus 4. Then du would be 2x dx, and we have a 2 there. I can do this U substitution like immediately in my head. I'm going to get 1/2 integral of, I'll have du out there. I'm left with 1 over square root u. It's u to the negative 1/2. That's a power rule problem. The integral of that is u to the 1/2. The integral of this is the square root of x squared plus 4. Hey, amazing. The trig substitution will work, and it won't be that bad. There's a sort of... It's not like a mathematical rule or anything, but in general, if there's an easy way to do it without the trig substitution, that usually means the trig substitution will turn out to be easy. Sometimes, like, the problem with trig substitution is if I'm gonna do a trig substitution, it's really hard to look at a thing pre-trig substitution and like know what trig function is gonna be left after the trig substitution. And even once, if you can, it's hard to imagine it and know whether that's going to be an easy or hard one. The difference between an easy trig integral and a hard trig integral is really finicky. And like cosine to the 4th is a real pain, but cosine to the 5th is real easy, and the difference is not clear. Let's think about this trig substitution real quick. If I'm doing x equals tangent theta, that means dx is secant squared theta. I get x is tangent theta here. Square root of, oh, it's going to be 2 tangent theta. So x squared plus 4 will be 2 secant squared. We get the square root of 4 secant squared will be 2 secant theta on bottom. Our dx is 2 secant squared theta. So a secant and a secant cancel, the 2 and the 2 cancel. We're left integrating 4 integral secant theta tangent theta, and yes, that's a very easy integral to do. Hey, heads up, this should be a very easy integral to do, secant tangent. That's the derivative of secant, which hopefully will turn out to be this. Maybe I'm missing some constants here. I'm doing a pretty sloppy job, but that's the big structure of how the integral's going to grow if you can do it. How would you do C? What would you try? Yeah, tabular or parts. Tabular is basically parts. It's the way to do parts repeatedly fast. Learning how to do tabular integration is sort of not that. Uh, you don't need to learn tabular integration if you're comfortable doing parts repeatedly, and you need to be comfortable doing parts at least once. If you learn to do tabular, though, the tabular method is perfect for this. You pick one side to take derivatives, x squared 2x2. You pick one side to integrate, e to the 3x, 1/3 e to the 3x, 1/9 e to the 3x. You need to keep doing these charts until you get a 0. And if you've gotten comfortable with tabular integration, it becomes really fast to write down your answers. This is going to be positive, this is going to be negative, this is going to be positive. The answer is going to be 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x plus a constant. Tabular is just parts repeated in a simpler format. Your exam does have a time limit, so being able to do them fast is valuable. Tabular is a really good thing to learn. The faster you can knock out the easy problems, the more time you have on the hard problems. But either way, whether you're doing it by parts or by tabular, you really want on the exam Monday to be able to look at this and say, great, I know exactly how to do that. I'm going to be able to do it the first try. Like, there's no question marks in my head. If you're able to notice the U substitution, that turns this problem into one of those as well. The U substitution that you can do on part A turns it into a power of U. You can see that before you even start writing the substitution. The best thing you can do is increase the number of problems that you see it and you say, I know how to do it, and I know the thing I try is definitely going to work. I can save this for later, or I can do it right now. I guess test taking advice, do those right now, because get the guaranteed points before you waste all your time on the points that you're not sure that you're getting right. Part B, what's the thing you would try on B? Let me copy this to a new page. So somebody try and do part B. Or everybody try and do part B. Do it, take a picture of it, post your attempt in the group chat. See how this goes. Let's let someone else do an integral, not me. I'll draw my cat, my little dog again. Wait, that's the wrong direction for the fingers to go. This dog is sleepy. I give this dog a cup of coffee. But hands are really hard. How do you draw a good hand? I guess you just look at your hand and see what your hand looks like and then draw that. Oh, that's a creepy, too human-looking hand. Gross. Guess I'll give it some fingernails. The fingernails look black. This guy's got the plague. World's best. There's no apostrophe in best. World's best. What's this guy good at? Trig substitution. This guy just woke up and he's drinking his coffee. But now he's drinking his coffee and he's awake. And he's doing okay. And he's shaved. And everything's gonna be okay. And there's less coffee in the cup because he's drinking it. Anyone got anything? Okay, can someone who's done something show how far they've gotten? Hopefully we all recognize that there's a trig substitution we can try here that'll get rid of the square root part. What does it turn into after the trig substitution? Is it gross? Is it hard? What do we get? Do I have a... Hooray! Someone sent an image. This is happening. Do I have a good... Let me go to my Gmail. That's the wrong Gmail. If I was smarter, if I knew where this was headed, I would have not linked my personal email to my Google Voice account so I could pull up this photo without showing everyone my personal email. Hey. Okay. Hi, you. Show me my messages. One of these... I have the messages. Are they in my arc? Well, that didn't work. Well... I guess I'll just write down what got sent in the picture. You guys can all see it anyway. That's the right trig substitution. X equals 2 secant theta. You get dx is the derivative of that is 2 secant theta tangent theta. That becomes x to the fourth is 2 to the fourth secant to the fourth. Square root of x squared minus 4 eventually becomes 2 tangent theta. It's technically 2 absolute value tangent theta, but you don't have to deal with that. And the d thing is 2 tangent theta, secant theta, d theta. The tangents cancel. The 2's cancel. You're left with 2 to the fourth integral of secant to the fifth theta. How would you do secant to the fifth? Oh crud, this is an odd power of secant. These are the hard ones. The worst we ever did in class was secant cubed. The bigger the odd power of secant gets, the worse this problem is. This is probably too complicated to be an exam question, but let's do integral of secant to the fifth. You gotta do it by parts. And I need to split off. When I have a constant out front of an integral by parts, I like putting it inside. Let's make it secant cubed theta, secant squared theta. We're peeling off a secant squared theta because that's the piece of the inside that we know how to integrate. I know the integral of secant squared, so that's what I want to be my dv when I do my integral by parts. Integral of u dv is uv minus integral v du. What do I want u to be? What do I want dv to be? dv is going to be secant squared theta. U is going to be everything else, 16 secant cubed theta. Du is 3 times 16 is 48 secant squared theta. Oh, wait, you don't have the d theta on it. This is where the d theta comes. Times derivative of the inside. What's the derivative of secant? It's secant tangent. V is the integral of this, is just tangent. I get equals uv. U times v is 16 secant cubed theta tangent theta. V doesn't have a d theta on it either. I'm trying to put d thetas everywhere. You do have a d theta on you. I'm messing all those up today. Okay, so uv is this minus the integral of v du. V du is going to be 48 secant cubed theta tangent squared theta, d theta. What do we do from here? From here, we recognize that tangent squared can be turned into a secant squared, which will give us back our original integral, which will let us move it to the other side and divide by something to solve for that integral. The trouble is we're also going to have an integral of secant cubed in it. We've done the integral of secant cubed before. You do it the same way. Again, you do the parts thing, move it over. So this is basically turning an integral of secant to the fifth into, well, I'm doing too much hand waving. What is tangent squared? Maybe you know this off the top of your head. I still have to write this down. Sine squared plus cosine squared is 1. Divide both sides by cosine squared. You get tangent squared plus 1 is secant squared. So tangent squared becomes secant squared minus 1. secant squared minus 1. I'm getting that 16 integral secant to the 5th equals 16 secant cubed theta tangent theta minus 48 integral secant to the 5th theta d theta. Minus makes plus 48 integral secant cubed theta. Move the 48 of the original to the other side. I get 16 plus 48. Is that 64? That is 64. Integral of secant to the 5th theta equals 16 secant cubed theta tangent theta plus 48 integral secant cubed theta. Divide both sides by 64. You become 1/4. You become 48 over 64 is 3/4. And now I just need to know how to do this integral. We've changed knowing how to do integral of secant to the 5th into needing to know how to do the integral of secant cubed. Doing the same trick on secant cubed will turn that into needing to know how to integrate secant. And we know the integral of secant. That one's worth memorizing. It's natural log absolute value secant plus tangent. Hey, here's a thing I said I would show you. The integral of secant, the first time we did it, we multiplied the top and bottom by secant plus tangent. It's this weird asinine trick that totally works because the derivative of tangent is secant squared, the derivative of secant is secant tangent. The top is now the derivative of the bottom. You do u equals secant plus tangent. You get the integral of 1 over u. You get natural log absolute value u is natural log absolute value secant plus tangent. I think this is worth memorizing. If you're integrating cosecant, it's the same thing with cos everywhere and a minus sign out front. That's a general rule, by the way, that any integral or derivative formula you learn about trig, the corresponding co-integral is the same co-integral, but with a minus sign. I don't know if you guys have noticed this. What's the derivative of sine? It's cosine. Well, what's the derivative of cosine? This is the co-version of that rule. I'm going to get the co of the answer. What's co-cosine? It's sine, but with a minus. This works for every trig, integral, fact, whatever, as long as it's purely trig. If you throw an x on here, that messes everything up. The reason for that is the cofunction identities or where they come from. I guess I'm not going to go into the cofunction identities. The thing I'm doing here, though, is I'm headed towards saying, when we did this, I said, hey, by the way, there is an easier way of integrating secant. I guess easier with an asterisk, because you need a bunch of tricks that we didn't know back then, but they're pretty easy tricks now. If I'm integrating 1 over cosine, it's reasonable to look at this and say, hey, that's an odd power of cosine. An odd power of cosine is something that was easy. Why was it easy? It's because you can pull off one of the cosines and end up with everything else is just about cosine squared. And you can do the same idea here. You end up with a negative even power of cosine, but you can still turn that into sines and get a reasonable trig substitution. Cosine squared is 1 minus sine squared. I can now do u equals sine theta, which I knew up front I was going to do because I pulled the cosine out with the d theta. du will be cosine theta d theta. This becomes the integral of 1 over 1 minus x squared. How do you do that integral? I guess this is the kind of thing that you might be tempted to try a trig substitution on, but that's going to take you exactly back to where you were. And it'll work. Or it'll work and turn it into the integral of secant. But we know another way to do this, which is as a... this is a thing you can do partial fractions on. And it's the easy kind of partial fractions. 1 minus x, 1 plus x. It's the kind of partial fractions where the cover-up method works completely. This is is going to be a over 1 minus x, b over 1 plus x. Is the cover-up method working for you guys? Have you done any of those? The thing I'm doing, I'll get my highlighter out to show off what I'm covering up. I want to multiply by, so first off, ignore the integrals that are there. I'm not thinking about the integrals. I'm thinking about this fraction is going to equal this fraction. I want to multiply both sides by 1 minus x. That clears this and clears this. And this thing will have a 1 minus x on it. And then I'm going to plug in x equals 1, which is going to make that into 0. So I'm plugging x equals 1 here. That gives me a. Plugging in x equals 1 here, that's a half. Our a value is a half. To get b, I want to multiply both sides by 1 plus x. If I multiply by 1 plus x, this is gone, and this all has a 1 plus x on it. And then plug in x equals negative 1, kills this. This becomes 0. Plug in x equals negative 1. I get 1 over 1 minus negative 1. That's 1 over 2. I get b must be a half. If you're good at the cover-up trick, this integral becomes something you can do real fast. It becomes 1 half 1 minus x, 1 half over 1 plus x. What's the integral of this? You get half. What's the integral of 1 over 1 minus x? Natural log absolute value 1 minus x. This thing has a constant on the x. You got to divide by that constant. Dividing by negative 1 gives you a negative out front. Plus, what's the integral of a half over 1 plus x? It's half natural log absolute value 1 plus x. This one just has a 1 on the x. I divide by 1, I don't get anything. Plus a constant. What was x? X was... Oh, these were u's. I said I was doing a u substitution. I guess that's going to be an x substitution instead of a u substitution. X was sine theta. Negative 1 half natural log absolute value 1 minus sine theta. Plus 1 half natural log absolute value 1 plus sine theta. There's a lot of... If you're using your calculus textbook to do problems, a thing that happens a lot is you do it, and you get an answer like this, and you look at the back of the book, and it's got an answer like this, and you go, what? This is not, I must have done something wrong. This is not the same function. This is the same function. Or if it's not the same function, it's off only by a constant. If I factor out the 1 half and switch the order, this is natural log 1 plus sine minus natural log 1 minus sine. There's a rule of logs that you can smush these into 1. I get natural log absolute value 1 plus sine over 1 minus sine. I guess I don't need these parentheses anymore. This still doesn't look like it. And there's a 1 half out front. Well, this thing inside the natural log... Did we talk about this? I think this might be a topic I failed to hit. Hey, when you're integrating, note 1 plus or minus sine theta and 1 plus or minus cosine theta. When you see these show up in an integral, and it's got to be a 1, these things are factors of 1 minus sine squared theta and 1 minus cosine squared theta. Each of these is a difference of squares. It factors into 1 plus sine, 1 minus sine, or 1 plus cosine, 1 minus cosine. And these things simplify into just one bit. When you have 1 plus sine, 1 minus cosine, anything like that, if you multiply it by its missing factor, it will turn into something that is, like now, only one thing. It's a sum or difference of a sine or cosine that you can turn into a perfect square. There's many situations where having two things added is worse than having just one thing. Bottom of a fraction is the perfect place to use this. I'm going to fix this fraction inside by sticking the missing part of the bottom. If I multiply the top and bottom by 1 plus sign, I get 1/2 natural log absolute value. 1 plus sine theta is all squared. And on bottom, that difference of squares foils into 1 minus sine squared theta. That thing's cosine squared theta. Hey, there's another rule of logs. A number out front of a log can hop up as an exponent. You get natural log absolute value 1 plus sine theta over cosine theta. Technically, square root of x squared isn't just x; it's absolute value x. Oh, there's already an absolute value. It didn't matter. Hey, split that into separate fractions. You get 1 over cosine plus sine over cosine. Sure enough, miracle of miracles, this turns into natural log absolute value secant plus tangent. If you're doing problems and you don't get the same answers, don't stress over that. These things have multiple answers. Cool. Alright, I'm going to put up a problem and ask you what's the best thing to try. If I have the integral of e to the square root x, try doing that. How would you do that? Go for it. Send me a picture of when you get something. Haven't gotten anything yet. I'm guessing that means no one's gotten it right. Can someone show me something they tried that didn't work? I forgot I was muted. Hey, I'm muting myself when I'm not talking because I feel weird about people hearing my swallows and sips. Give me a heads up if it seems like if I forget to unmute. You really love a trig substitution where the derivative is the thing outside. What's the derivative of square root x? It's 1 over 2 root x. I don't have a 1 over 2 root x out there. So it's sort of tempting to say this is not a good idea. But in the absence of things that are better ideas, you try the thing that's not a good idea. If u is root x, that becomes x is u squared. I can rewrite that as dx is 2u du. This I talked about in the first day of streaming, saying that it's your ability to force a substitution to go through even when it doesn't feel like it's going well. These are the same thing, by the way. It's not obvious these are the same, but they are. If I move this to the other side, I get dx is 2 root x du. Well, that's what 2u is. So these are telling us the same thing, but one goes smoother than the other. This becomes e to the u times what's dx? Dx is 2u du. This is 2 integral u e to the u du. And this is a problem where you say, hey, I know how to do that. You do that by parts. And it looks like that went correctly. Cool. Let's try. How would you do? The integral of the square root of 1 minus x over 1 plus x dx. Take a shot at doing this. Try something, and if your something doesn't work, send that. Okay, the hardest part of this for me is knowing when I've let enough time go by. Has anyone gotten anywhere on this? Anyone had any ideas? I've been Googling interesting integrals. And I'm tempted to just sort of get sucked into that and let people keep working. But I haven't heard anything in a while. And I can't look around and see if people are looking like they're making progress. What have you tried? Anybody? I'm not hearing anything. I guess I'm going to talk about it then. They don't have anything they tried that they think is worth showing. I guess before I start talking about how you can try this. Should I give a hint? To me, the thing I notice when I look at this is the same deal as that 1 plus sine, 1 plus cosine, 1 minus sine, 1 minus cosine. Like this kind of has that going. Ooh, I got an image. What somebody said. Oh. I think this is right. So, let's see what... Who sent this? Caleb sent this again? So a lot of things got tried at the start, but it looks like the thing that went somewhere was trying x equals sine theta. Oh, multiplying the... It's okay, so yeah. Multiplying the top and bottom by a 1 minus x inside the square root. It's good for the top because it turns it into a perfect square. 1 minus x squared, square root of that is just 1 minus x outside the square root. I guess technically there's absolute values, but I usually ignore those and deal with them at the end. Or I guess more specifically, don't deal with them at the end. Bottom, you FOIL it out, you get square root 1 minus x squared, and this looks like the type of thing we can do a trig substitution with. The good trig substitution is x equals sine theta. It turns into 1 minus sine theta over square root 1 minus sine squared theta dx is cosine theta d theta. 1 minus sine squared becomes cosine squared. Square root of that is cosine. Cosines cancel. This is just the integral of 1 minus sine theta? Oh, this seems different than what Caleb got. This feels wrong. Oh, okay. Yeah, you're doing, I think, a right thing. But you have secant times cosine there and aren't immediately canceling them. Yeah. Secant times cosine is 1, so that just goes away. I think there might be a mistake in your last steps, but I don't think it's worth... I don't know if it's worth spending the time on that. This becomes theta minus negative cosine theta. Cosine theta is... According to the trig substitution, x equals sine theta. That's sine inverse of x plus cosine theta is square root 1 minus sine squared. So that's 1 minus x squared plus a constant. I guess you're doing a trig substitution to work that out, but I know how to turn a cosine into a sine without doing that reference at triangle junk. Square root, yeah. Here's an integral I love. 1 over 1 plus e to the x. Take a shot at this. I'd love to get a response from someone who's not Caleb. Oh, I should... Do I... Oh, dang, I'm not muted. I meant to be... Anyone got anything? Um... So, yeah, this one's tricky. The most... I feel like the plainest, obvious thing to try is let's just try the u substitution u equals e to the x. Maybe try u equals e to the x plus 1. Usually if you're doing a u substitution, at least the kind of substitution where you see the du out there, then throwing on the +1 onto your choice of u is nice because it doesn't make the du any worse, and you can kind of soak up more of the problem. This isn't that kind, though, because I don't have the du out there to soak it up, and not having the du will make the other things worse. If u is e to the x, because I have to force the substitution, this is a good place to solve for x. X is natural log u, so dx is going to be 1 over u du. What does this integral turn into? It's the integral of 1 over 1 plus u dx is 1 over u du. Is this doable? It's 1 over u plus u squared. Alright, staring at this, you can do a trig substitution that you'll have to complete the square for. I don't want to complete the square. Like, it's not bad, but actually, is that worth trying? I don't know what that's going to do. Let's try that. U squared plus u, leave a blank. I want to take this and cut it in half, and then square that. I'll get plus 1/4 minus 1/4. That becomes u plus 1/2 squared minus 1/2 squared. What trig substitution this suggests? That's a secant one. I want u plus 1/2 to be 1/2 secant theta. So du is going to be 1/2 secant theta tangent theta. How bad is this thing going to be? U plus 1/2 squared minus 1/2 squared is going to be 1 over 1/4 secant squared theta minus 1/4. Factor out the 4th, I get secant squared plus 1 minus 1. That's going to be tangent theta. Or tangent squared theta. I get 4. 1 over 1/4 is 4. With that 1/2 there, I get 2 is the... Let's clean this up. Don't be so sloppy. I get real sloppy because I get excited about doing integrals. This becomes a 4, that's a half, I get the number 2. Secant squared minus 1 should be tangent squared. Yes. Secant theta, tangent theta over tangent squared theta. A tangent cancels with a tangent. This is 2 integral secant over tangent. I have an odd number of tangents, but I think that's going to turn into the other thing. Is this doable? Let's just turn those into sines and cosines, see what we got here. Secant is 1 over cosine. Tangent is sine over cosine, that's cosine over sine. Ooh, that's doable. I get 2. The cosines cancel, I'm left with 1 over sine. This is cosecant. I recommend knowing the integral of cosecant off the top of your head. It's natural log absolute value. So for secant, it's natural log absolute value secant plus tangent. For cosecant, it's going to be cosecant plus cotangent with a minus. This is doable, this is gross. I'm going to stop doing this here. Like, that worked, but I don't think that's the nice way to do it. Let's go back a second. A second ago we had it as this point. There's a much easier way of doing this one. It was u plus u squared. That bottom factors. That's u times u plus 1. This is like that's a polynomial on bottom. Usually we think about partial fractions when, like, this doesn't look like a partial fraction situation, but it totally is. 1 over u plus 1 can be broken down as a over u plus b over u plus 1. If I imagine multiplying both sides by u and then plugging in u equals 0, I find that, let's do my stupid cover-up thing, Multiplying by u gets rid of this, gets rid of this. Plugging in u equals, this thing will have a u on it, but then plugging in u equals 0 makes this go away. I get a as 1. If I multiply both sides by u plus 1, and then plug in u equals -1, what am I going to get? That would be cover up. U plus 1 goes away. This has a u plus 1 on it, and then when I plug in -1, it goes away. So I just need to plug -1 into there. I get b is -1. Ooh, ooh, ooh. I just got a message from Jay, who is Joe. What went wrong with this substitution? I think you're off by a minus sign. When you did the partial fraction split up, I'm getting that the b thing should be -1. So it should be integral 1 over u minus 1 over 1 plus u. So it's natural log absolute value u minus natural log absolute value 1 plus u. And u was e to the x. Is, I think, all you're off by. That works. Let's keep doing it, though. 1 over 1 plus e to the x. I like this problem as a pet because there's a million ways to do it. Almost everyone I know kicks themselves when they see when I write plus e to the x minus e to the x. I can write that as 1 plus e to the x over 1 plus e to the x minus e to the x over 1 plus e to the x. Like, you look at the problem and you say, man, I wish there was an e to the x on top. And this is a clever way of doing that. The integral of 1 minus, do the u substitution here, the integral of 1. It's very clear how I'm going to get x minus natural log 1 plus e to the x. That's another way at it. Hey, let's not stop there. If you multiply the top and bottom by e to the negative x, you get e to the negative x on top, and you get e to the negative x plus, what's e to the x times e to the negative x? 1. You get basically the same thing, but negatives instead of positives. Don't care too much about that. But you have that extra thing on top. You get negative natural log absolute value 1 plus e to the negative x, which, if you do some rule of logs, will turn out to be the same as the other thing. Like, the hiding logs hide weird substitutions you can do. There's a million ways to do that problem. I like that problem for having a million ways to do it. How would you do the integral of root x times 2 minus 3 root x? Take a shot at that. I got a submission! That took a long time. We're using u equals root x. I'll take it from there. That makes x equals u squared. Dx is going to be 2u du. So this should be u, 2 minus 3u, times 2u du. Is this how this went there? Oh, yep. You made a mistake differentiating u. If u is root x, then du is 1/2 x to the negative 1/2. On the photo I'm looking at, you integrated instead of differentiating, which is going to mess things up. You do the substitution, you get a polynomial. That's 2u squared, 2 minus 3u. You distribute things in, 4u minus 6u squared, and you can do that. I don't know who else did this in a similar way. This is way overkill. This is the kind of integral it's fun to show Cal 2 students once they've learned a million tricks and forgot that they knew how to do this in Cal 1. Just distribute that. That's 2x to the 1/2 minus 3x. Use the power rule. 3/2. Oh, my thing's about to crash. Yes, recover the note. Yes, yes, yes. Yeah, you FOIL it out as the power rule. It's 2x to the 1/2 minus 3x. It's x to the 3/2 times 2/3 makes 4/3 out front. Integral of that is 3/2 x squared. Yeah, that's it. The more tricks you learn, the more you lose the ability to notice when a problem is easy. Practice noticing when problems are easy. Let's try this one. Well, yeah, let's do this. Integral of secant x over sine squared x. What would you try here? Alright, we're getting close to 6, and I haven't heard anything, so I'm going to start doing this one. I'm going to stop talking at 6, by the way. Or maybe a little after 6. I'm going to do this one, and then I'm going to show you a problem that's worth doing between classes. Let's see. Turn this into sines and cosines, maybe? I can write this as sine squared times cosine x. When we did our big talk about trig stuff, we made a big deal about it's really good to have an odd power of sine or cosine. And the thing you have an odd power of, you should pull one out of with the dx. This is not quite that situation, but the same principle might be a good idea. If I think about pulling a cosine x off to be out here, what am I integrating left with? Well, I need to, if I put a cosine with the dx, I need to divide by another cosine out here. So I'll get sine squared, cosine squared in the bottom of the fraction. And the same reason that pulling off the cosine x is a good idea is still a good idea here. I can do the substitution u equals sine x is the thing that will make du be cosine x dx. This guy is u squared, and cosine squared is 1 minus sine squared. So I can write this as 1 over u squared 1 minus u squared du. And this is a good partial fractions problem. I get 1 over u squared 1 minus u 1 plus u. And this is correct, but having this 1 minus u always feels goofy to me. I prefer writing this as negative 1 over, change the 1 minus u to a u minus 1. You're just changing the sign. And I want to split this up into partial fractions. And we can't quite use the cover-up trick to do all the work here. This should be a over u, b over u squared, c over u minus 1, d over u plus 1. How much work can the cover-up trick do? If I multiply by u minus 1 and then evaluate that at u equals 1, that'll tell me that c equals, cover that up and plug in 1, negative 1/2. If I multiply both sides by u plus 1 and then plug in u equals negative 1, that'll give me d. Cover that up, plug in negative 1, I get negative 1 over 1 times negative 2. I think I'm getting d is positive 1/2. If I multiply both sides by u squared and plug in u equals 0, cover that up, I'm going to get b is plug in 0, negative 1 over negative 1 times positive 1 will be 1. And I don't have a way to get a with the cover-up trick. I haven't mentioned this before. If you can get all but one of the letters using the cover-up trick, you can get that last letter by plugging in any other number. If I am correct that negative 1 over u squared u minus 1 u plus 1 does equal a over u, b over b is 1, so 1 over u squared, minus 1/2 over u minus 1 plus 1/2 over u plus 1, then plugging in u equals anything gives me something I can solve for a that's pretty easy. I'd like to plug in something that's not too hard to plug in. I guess I'll plug in u equals 2. Maybe 1/2 would be good. I don't know, I'm going to go with 2. I get negative 1 over 4 times 1 times 3 equals a over 2 plus 1/4 minus 1/2 over 1 plus 1/2 over 3. And this is reasonably not too difficult to solve for a. It feels easier than doing the full partial fractions thing. Negative 1/12 equals half a plus a fourth minus a half plus a sixth. I guess I'm going to put everything into a common denominator of 12. Well, half a equals negative a twelfth. Move this over, I get negative a half. Wait. Oh, I wrote the wrong thing here. I should have written a fourth here. So, minus a fourth is minus 3/12. Plus a half is plus 6/12. Minus a sixth is minus 2/12. Negative 1, negative 3, negative 2. Is this 0? What? Half a equals 0? So a is 0? I guess that's possible. That's unexpected. I am surprised to get that a equals 0. I'm going to assume that we did this right, because every time I check my partial fractions and it's wrong, my soul dies a little. I'm going to assume we did this right. If we didn't do it right, you can do the full standard partial fraction decompositions and solve something. And apparently a is 0, so that usually makes these things easier. So the thing that I'm trying to integrate can be rewritten as, that one goes away, integral of 1 over u squared plus minus a half over u minus 1 plus a half over u plus 1 du. It's negative 1 over u minus a half natural log absolute value u minus 1 plus a half natural log absolute value u plus 1. Substitute in u equals, what was u? U was sine x. This is doable. I'm shocked that that thing was 0. So let's see, where are we? I'm going to post the practice exam tonight. I'm also going to post some solutions to the homework problems. Hey, heads up. I'm going to put... hopefully everything I say out loud now I'll be posting on Blackboard so you can read a more official version and not have to watch to the end of a YouTube video to know the things about the exam. The exam's going to be Monday. I'd like to put the exam 4 to 6. I will ask you guys, or I will post on Blackboard asking you, hey, are you free from 4 to 6 on Monday? I want to do it synchronously so I can just write one version of the exam. Practice exam will go up tonight. What was I saying? What the? You completely lost track of what I was trying to say. Oh yeah, I'm going to post some solutions to the homework problems. Hey, here's a fact. I'm going to post like my solutions to most of the homework problems. I wrote them up before, so I have a thing I can post. It may not include every problem. If there's problems missing, let me know, and I'll go back and insert them and repost, but I think it has all of them in basically the correct order. I might also add a couple more homework problems if I get ambitious enough. I feel like there should be a cosine squared and a sine squared in there that I didn't see. Maybe I'll go through the solutions and see if a thing turns into sine squared and it's not obvious in the problem, but some even powers of sine and cosine are necessary. While I was sitting here waiting for you guys to do problems and Googling interesting integrals, I saw the best integral. Do this integral. X squared, x to the fourth, 1 minus x to the fourth over 1 plus x squared. And integrate it from 0 to 1. And doing this is not a tricky or fun integral, but the answer is hilarious. Trust me, if you do this integral and you get it correct, the answer to this integral is very funny. Let me double check that I wrote the right problem down. I did. I'll show you how to do this integral, and I'll do the first step for you. You got to evaluate it from 0 to 1 to get the punchline. This is not a hard problem. Like, this is a standard partial fractions type deal. You don't even have to split up the partial fractions. The issue is just the step 0. The top is bigger than the bottom. So you're going to need to do long division. To do long division, you're going to need to FOIL out the top. When you FOIL out the top, it's x to the 4th times. What do you get when you raise something to the 4th? Why do I have sine squared and cos? Oh, I was talking about integrals I should put. This is the binomial thing that comes from Pascal's triangle. I don't know if you've seen this in another class. I feel like this is the kind of thing you're supposed to see in Cal 1. I haven't taught Cal 1 in a million years, so I don't know if they still cover that. When you FOIL out 1 minus x to the 4th, you can get there by 1 minus x squared. Squared is like how to FOIL it in 2 steps instead of lots of steps. You're going to end up with 1 minus 4x plus 6x squared minus 4x cubed plus x to the 4th. You distribute in the x to the 4th, you get, I'll switch the order up, x to the 8 minus 4x to the 7 plus 6x to the 6 minus 4x to the 5th plus x to the 4th, divided by 1 plus x squared. Alright, I dare you, between now and next class, do the long division that you need to do. Do long division, integrate what you get. You're going to get a polynomial plus some x plus something over 1 plus x squared. This integral is easy to do. Ax over 1 plus x squared, b over 1 plus x squared. This is an easy substitution, u equals 1 plus x squared. This is you don't even need anything. This is b tangent inverse x. The answer you get, though, when you evaluate it from 0 to 1 is just hilarious. And I think it's worth doing. If you're ahead on the homework, try and do this. Exam's going to be Monday, hopefully 4 to 6. You want to get all the homework done by Monday. I'm going to post all solutions to the homework. Oh, that's what I meant to say. Hey, it is a fact that I am aware of that if I post all the solutions to the homework, you are capable of just writing down those solutions and turning that in on Monday. And you're not going to get in trouble. Like, that's a thing you're allowed to do. I'm not going to stop you from refusing to learn anything in the class. It's not a great idea. You know, try and do the problems. That's what they're there for. Cool. I'll see you guys tomorrow, 4 to 6. If you're able to tune in live, I'm going to try and do something similar to this. Actually, no. Tomorrow I'm going to talk about the practice exam. Yeah, I'm posting the practice exam. Take a look at that. Feel free to send me questions you have on the homework problems, like anything this class can be useful for. I'm out of lecture material. I'm going to show up tomorrow and Friday to do examples. If you have problems from the homework you want to see me do, let me know. I'll see you around. Take it sleazy.